Hey everyone, my name is Zachary Gorm, and today I'd like to talk about simple harmonic motion and focus on the pendulum. What we define as simple harmonic motion is a simple system that undergoes repetitive motion due to the damping force proportional to the distance from equilibrium. That was a lot of words, but what does it mean? Here is my pendulum that I'm using today, and what I meant from before is that if I hold it right here, it doesn't rock back and forward, it just stays in place. But if I move it to the side, there's a force from the string that causes it to rock back and forward and back and forward and back and forward. There are three important concepts to understanding a simple pendulum. First of all, there's a fixed point required. Here I have my yo-yo, my string, and a connection point. That was my hand earlier, but that can be anything. Second of all, there's a force of tension towards the string always. The string can't push anything, so it can only pull. Therefore, no matter where the force of gravity is pointing, the force of tension has to be towards the connection point. Third of all, the motion is driven by gravity. If I have a spring and I bring it to space, it will still try and go towards equilibrium no matter what. But if I don't have gravity, then a pendulum will not work. We need to talk energy. The two types of energy we're using are potential and kinetic. As you start at the highest point, you have entirely potential. There's no moving part. But as you let go and it gets down to the bottom, it turns into entirely kinetic energy. And then as it rises up again to the other side, you now have entirely potential energy again as it stops over there to now go the other way. Gravity and tension work together to cause the periodic motion of the yo-yo. If I start right here, I take that to be a potential of 0 because nothing moves. But if I move up here, I've raised the yo-yo, therefore it has an increased potential. So if I let go of it, then it will have a gained kinetic energy right here, and the potential will be 0. And then back here, the potential will be high again, and the kinetic energy will be 0. So therefore it'll rock back and forward like that. Now we can look at the forces acting upon the pendulum. As you see here, the force downward is gravity, which is equal to mg. And then if you look at the force of tension, we can break it into force of tension sine theta and force of tension cosine theta. And then using the x and y coordinates shown here, we can state that the f of y is equal to ft cosine theta minus fg, and the f of x is equal to ft sine theta. We need to make two assumptions to be able to solve this problem. First of all, we need to assume that theta is small enough that you can do small angle approximation. What that means is that you can make cosine theta approximately equal to 1 and sine theta approximately equal to theta in radians. Second of all, we need to assume that the force in the y direction is approximately 0. This is because our change in y is significantly less than our change in x at a low theta, and therefore the force in that direction would be negligible. We can use those two assumptions to change our f of y and f of x. Originally we have that f of y is equal to the force of tension times cosine theta minus the force of gravity. But now that becomes that the force of gravity is approximately equal to the force of tension. The f of x is equal to ft sine theta, and we can change that now into that f of x is equal to mg theta. Well, using Newton's second law, we can say that the force in the x direction has to equal the mass times the acceleration in the x direction. We can take that and put them together to equal that the acceleration in the x direction is equal to g, the gravitational constant, times theta. Looking at our original angle of the pendulum, we can see that sine theta is equal to delta x over L, where delta x is the movement in the x direction and L is the length of the string. Therefore, if we do the same approximation, we can say that the theta is approximately equal to delta x over L, now making our ax equal to the gravitational constant times the change in the x over L. For a simple harmonic oscillator in the x direction, we define the acceleration as the angular frequency squared times the change in x. Taking that in our previous equation, we can combine them and say that the angular frequency squared is equal to g over L. Using the definition of angular frequency, which is 2 pi over the t period, we can now state that t is equal to 2 pi square root of L over g. But what does that mean? That means that we don't have a mass or theta dependence for our period, which is crazy to me if you think about it. The period is equal to 2 pi square root of L over g. That means that the only two things that can affect the period are the length of the string and the gravitational constant. The length of the string, if you increase the length, would increase the period. And then the gravitational constant, if you increase the gravitational constant, you would decrease the period. That means that if you change the mass on the string, or if you change the initial angle of let go, within the small approximation region, it would not affect it much at all. Introducing my budget setup. What I'm going to do here is I'm going to change the angle from theta 1 and theta 2 and change the length of the string from 15 centimeters to 25 and measure 10 periods to make sure that the thing that we have derived previously is correct. So tilting it back to theta 1, we measure 10 periods starting now. Alright, 7.87 seconds. Alright, so clearing that, and we change to theta 2. Ready, go. $7.96. That is not much of a change at all. Let's see how changing the string changes it. Now for the same test using a 25 centimeter string. Ready, go. $9.52. Going to theta 2, ready, go. $9.46. Here you have it. Whenever you look at theta 1 and theta 2 for a length of 15 centimeters, you find that they're almost identical. And the same thing for the length of 25. But whenever you look at the difference between the two, you find about 2 seconds difference. Therefore, we know that the length affects the period rather than the theta. There we have it. We found out that our derivation actually has real-life results. So thank you for watching. I hope you learned something new, and have a great day.